When you work this out, you find that the velocity here is 0.5 meters per second. Is this possible? No, this is not a possible outcome. Now, making up a problem is one thing. Making up a problem that has realistic outcomes is another. But this can't work. And for those of you who are still like, I don't understand, how can this one be going 4 times faster than this one and still be behind it? That's why this doesn't work. This is not a possible outcome. It would be a possible outcome if this cart tunneled through the other cart. So if we're talking like a bullet being fired through a block of wood, then that might be a realistic outcome. But for 2 carts on a track, this wouldn't happen. So just because there's a mathematical way to get an answer doesn't mean it's a logical or realistic solution. Does that make sense? The problem with conservation of momentum problems in general is that they rely on more information than we have. If all we know about is the momentum of the system, then during the collision, we don't know what kinds of things are going to contribute to the final outcome. In a true inelastic collision, we have 2 possible answers, not just 2, I'm sorry. We have 2 velocities that we have to solve for. Momentum doesn't really give us enough information to figure them both out. There are ways for us to figure them both out if we know more about the problem. For example, they could tell us how much energy was lost during the collision. That would give us more information. They could tell us other things too, like they could tell us it's a perfectly inelastic collision. Now that's giving you a specific piece of information. And I'm giving this to you and asking, do you know what to do with that piece of information? If I tell you that this collision is perfectly inelastic, could you solve the problem now? Because I've given you more information. Please try. Okay, believe it or not, that's enough time for you to know what to do. Maybe not execute it all the way, but enough time to know what to do. So, do you realize what you have to do if it's perfectly inelastic? Can somebody tell me? Yep.
Both objects will stick together.
The objects stick together. What's the implication of the 2 objects sticking together? Yes, we stop. Yes, but something else. Go ahead.
They'll have the same velocity.
They have the same velocity. That's the implication. That they're going to stick together, they're going to have the same velocity. That reduces the number of unknowns, and that makes it a problem that you can solve. So sure, we back this guy up, put him over here. They are now one object with a combined mass of 1,500 grams, and they have the same velocity. That's how you solve this problem. That is a perfectly inelastic collision. Of course, there is another possibility. What if I tell you that this is an elastic collision? Could you find the answer then? Now, I don't want the answer. I want you to set up the answer. Can you set up the problem where I say this is a perfectly elastic collision? You don't need the word perfectly there, it's redundant. Perhaps your notes need to help you better. There are 3 kinds of collisions. There's a category called inelastic. We covered that. There's perfectly inelastic, stick together. And then there's elastic collisions. In an elastic collision, momentum is conserved and kinetic energy is conserved. So we have the standard momentum equation where I'm going to have 500 times 3 plus 1,000 times 0 equals 500 times its unknown velocity plus 1,000 times its unknown velocity. This can't be solved for V5 or V10 because we don't have enough information. But the moment you know it's elastic, you can generate another relationship. In an elastic collision, momentum and kinetic energy are conserved. So now 1/2 times 500 times 3 squared plus 1/2 times 1,000 times 0 squared equals 1/2 times 500 times v5 squared plus 1/2 times 1,000 times v10 squared. That generates two equations and two unknowns. You could solve this. Well, it can be solved. And you know why I'm saying it that way, right? When you look at this, could you solve it? I mean, it's not particularly straightforward. Now, there's some things you can do in this particular example that would help, like I could divide out by 500 and make that 3 equals VS plus 2 V10. Not VS, V5. That's just me dividing out by 500. In the second one, I could cancel all the 1/2s. And I could divide by 500 again and get 3 squared equals V5 squared plus 2 V10 squared. Right? This is just because the masses were multiples of each other is why I can reduce it. But I still am not convinced that all of you will be okay here. It's not straightforward. I probably have to solve this for V5 and then plug that in here and solve for V10 or something like that. Right? It's two equations with two unknowns is all it is. But you understand that this is going to be quite laborious, isn't it? A lot of labor involved. I'm not going to spend a lot of class time doing this. And the blank looks on your faces make me scared that you can't do it. So you should. You should do it. I'm not going to use the class time, but you should. The likelihood that this would be on an exam is relatively low, but not zero. And this is just a math problem. In fact, I would probably have your calculator do it. I will give you one hint, though. These are generally factorable because you have a solution. Right? It's going to generate two answers because it's a quadratic. You understand that all quadratics generate two answers, right? If you look closely at this, one of your answers is V5 equals 3 and V10 equals 0. That has to be an outcome because those were the original velocities that we started with. So you have a place to start factoring because one of your factors is going to have to be -3 for V5 or 0 for V10. But this is a math problem. This is the physics portion. There's something else I'd like you to be able to do, and I'm not sure you can. So I want to ask you. This one proved a few things to me that I'm a little concerned about, but I'm willing to continue. Can you find the velocity of the center of mass of the system? We talked about this yesterday too. It's not much here, but this is where we start talking about the system. The momentum of the system is the sum of the momentums of all the objects. This is for any system. So if I have a system of n objects, then I just add up all the momentums. It's a vector though, you have to keep that in mind. So I add up all the momentums. So that's just me taking momentum 1 and momentum 2 for each object that I have all the way till I get to the last object. By definition, that has to equal the mass of the system times the velocity of the center of mass. I said it, but it was quick yesterday. But this has to be true. We have individual collisions that take place, but the velocity of the center of mass stays constant. And there's something I was saying about impulse related to this. You have just two objects here. 500 times 3 plus 1,000 times 1 equals 500 plus 1,000 times V center of mass. But I've made a mistake. Although I told you what you needed to consider, I didn't do it myself. What is it? Right. It should be -1 because these are vectors. And so if I make the 3 positive, I have to make the 1 negative. Vectors. So this would tell us the velocity of the center of mass. Now, not tough here. I'm going to have my 1,500 minus 1,000 is 500. I'm going to divide by 1,500. So I get that the velocity of center of mass is 1/3 of a meter per second. After these two cars collide, what will be the velocity of the center of mass? Well, that makes me sad. A few of you are trying to say it, but just don't have the courage. It won't be 0. It'll be the same. I mean, I just said it a minute ago. If there's a collision, it doesn't change the velocity of the center of mass. The only thing that can change the velocity of the center of mass is if an external force acts on the system. That was the whole point of the concept of impulse. Impulse is the only way you can change the momentum of anything, even a system. So if you have a system of particles, the only way to change the velocity of the center of mass is if a force is applied to the system. Now there can be collisions, but this car will have a change in momentum that is equal and opposite to this car. That's what we did yesterday. Showed that the change due to impulse has to be the same for both because of Newton's third law. That can't change the velocity of the center of mass. Something external to the system is the only way to change the velocity of the center of mass. Worth putting in your notes. So I fire a bullet at a block of wood's at rest. I do it 3 different times, 3 different things happen. In one case, the bullet bounces back. It's dangerous. In one situation, it passes through. And in one situation, it gets embedded. Everybody understand all 3? For every collision, calculate the velocity of the block and calculate the velocity of the center of mass of the system. And do that for all 3 situations, please. This is the practice. I'm giving this to you because I want you to be good at this. And one of your homework problems is modeled just like this. In looking at the one where it gets stuck, the bullet will be inside this block and they will both have a combined velocity that is the same for both. The momentum of the bullet is 0.015 kilograms times 300. The momentum of the block is 0 because it's not moving. After the collision, the 1 kilogram block and the bullet have a combined velocity that has to be the same. So the 300 times 0.015 is 4.5. So this side is 4.5. And that equals 1.015 V. And divide both sides by 1.015, and that's where I get 4.4 meters per second. Which, by the way, is the same as the velocity of the center of mass. It has to be because they're now one object, so they have to be moving at the velocity of the center of mass. Is there any other one of these you'd like me to perform? All right. So you notice that we've been dealing with all one-dimensional examples. Doesn't have to be one-dimensional. There's absolutely no reason why we couldn't extend this to a system where one object strikes another object and the result is a 2-dimensional answer. Although I have no intention of spending much time on this, the likelihood of a problem is not high. It's not zero either. So I think that you could probably all agree that if you have one like billiard ball and you strike another, it's likely that they'll go off at some kind of angle. So that's what I'm imagining right here. So you have one moving and one at rest. After the collision, one of them goes off in one direction, say this way, and the other one goes off in a different direction. If anybody's played, pool, you kind of get an idea that this can be influenced by stuff like if you spin the ball or other things like that. What is important to understand about this problem is that it still obeys all of the same rules. If I divide this up into before and after, where this is where we were before, and this is after. The rules of momentum still apply, even though it's two-dimensional. So before the collision, all of the momentum was in one direction because only one object was moving, which is probably the extent of what you would have to do in my class. So the first thing I would tell you is to, like anything else we've done when it comes to things that have direction, is pick a direction that you call X. And that means the perpendicular is the Y direction. Before the collision, just the green ball had momentum. And its momentum is mv in the X direction. In the Y direction, the momentum was 0. Right? Because it wasn't moving in the Y direction at all. So whatever direction the first object was moving, that's the X direction now. And the momentum is in that direction. What that ultimately means is that after the collision, whatever momentum is in one direction in the Y direction, this is the momentum for the red ball in the Y direction, there would have to be an equal amount of momentum in this direction so that the total momentum in the Y direction is 0. That's what it comes down to. That if they're going to be knocked at an angle, this momentum and this momentum have to be equal but opposite. It's the only way the Y momentum equals what it was before. At the same time, the red ball has an X momentum in this direction, and the green ball has a extra momentum in this direction. These two momentums, the red ball in the X direction and the green ball in the X direction, they have to add up to equal whatever the momentum was of the first ball all by itself. These are mathematically complicated, as you can probably imagine, and have lots of geometry involved because there'll be an angle on this side and an angle on that side, and they don't necessarily have to be the same, especially if these objects have different masses and it's an inelastic collision. There's no telling how they will respond to this. I won't expect you to have to do any of this before the end of the semester. We will come back to this second semester. I will expect that you could be able to recognize that these two momenta have to be equal but opposite. I will expect that you can that you could recognize that. And I'll expect that as soon as Friday. There's not much to think about there, which is why I'm okay with this problem, just kind of putting it out there in front of you. I'm going to combine what we just did with what you're going to be expected to do this Friday. So So I want to set up my first example. It's called a ballistic pendulum. And this is a super common example. The idea is that a bullet is fired at a block that is just hanging there. The bullet becomes embedded in the block, and the whole system swings upwards in angle theta. The idea of a ballistic pendulum is that if the masses are known, you might be able to figure out how fast the bullet is going by measuring the angle that this makes. That's the idea of a ballistic pendulum. It's a simple way of measuring the speed of bullets. It's one way that you can make one, put it outside if you're at a range. This is how they could measure it. It's not terribly inaccurate. It works pretty good. There are more accurate ways to do it. But the ballistic pendulum problem comes in kind of two flavors. This is the first flavor, where an angle is created between the block and the vertical. The other flavor involves using a spring. We're going to look at both. The problem here isn't that the material is particularly challenging. The problem is knowing when to use which, well, you would say when to use which formula, because that's your favorite way of saying it. There's a formula that covers this. There isn't. It's when to use which principle. And there's a piece that's been left out on purpose. And they'll do this on your problem. They will leave out a piece. They will show the before case and this after case, and leave you to figure out what happened in the middle. So let's talk about this particular problem and what happens in the middle. In the middle, there's a collision. A point where the bullet strikes the block and the bullet and block acquire a new velocity. You see, this problem has to be broken up into steps. The first step is the collision. The bullet imparts momentum to the block, but the block and bullet just begin to move. The next part is once they start moving, suddenly they swing upwards, so now we have an energy problem. Your job is to know when do you apply conservation of momentum and when do you apply conservation of energy. And that's what I want to help with. The collision portion of this problem, the collision portion, is the instant just before contact and the instant just after contact. Said this yesterday. And this is why I said this to you yesterday. If you didn't put it in your notes, put it in there now. This is the instant just before contact, and this is the instant just after contact. That's the collision. During that time, the momentum is conserved. Whatever the momentum of the bullet is, becomes the momentum of bullet and block together. The reason we say the instant before and the instant after is the moment after this happens, the block starts to swing upwards and we start getting a conservation of energy problem. The moment after, there's kinetic energy here. And if the bullet and block come to rest because an external force acted on our system, then we'll have gravitational potential energy here. This problem has to be done in two parts. And it's important to understand where one part ends and one part begins. In this particular problem, the collision happens first. So mass of the bullet times the velocity of the bullet is going to equal the mass of the block plus the mass of the bullet times their final velocity after the collision. In this problem, the collision happened first. Now, that immediately leads to the next part of the problem. And the next part of the problem is that this velocity creates kinetic energy for the bullet block system, meaning we have 1/2 mass of the bullet plus mass of the block times V final squared. That's how much kinetic energy our system has. And that kinetic energy is going to cause our pendulum to swing upwards, which is going to slow the pendulum down until all that energy is converted into gravitational potential energy. In fact, you're supposed to remember that H is based on the angle. This is the kind of problem you're going to be expected to do. And I find that the hardest part is knowing when to apply one conservation rule or when to apply another. And to not forget that there's absolutely no reason we couldn't ask, what is the tension in the string right after the bullet and block move together, because that would be circular motion and that would be a centripetal acceleration. And if you put all three of those together, now you're beginning to get an FRQ, because that's what they're going to do your entire semester in a single problem. Now again, I'm not giving you a problem here. I'm showing you what these problems look like. Are you writing down enough notes? Because this is one of the homework questions. Here's the next one, like this one. If not, the homework questions you have are straight off of old released exams, so I don't have to make these up. And there's no reason to make them up. In this one, it's a relatively old one. I chose it because it's pretty straightforward, I guess. A bullet strikes a block. The bullet block system is eventually going to make it through the loop. In these problems, they generally ask, how fast does the bullet have to be shot so that the bullet block system successfully makes it through the loop? This one's a toughie. You have to understand what they're telling you. There's three parts to this problem. So let's start recognizing they gave you an if. What does it have to do to successfully make it through the loop? If it makes it through the loop, net force had to equal MAC. That's where you would start. Put the block at the condition. There's the condition. To successfully make it through the loop, the bullet and block together have to meet this condition, which means mg plus n equals mv squared over r. The minimum speed is when that normal force goes to zero. This is not new. We've talked about this problem. Now we back that up. Right there, there's gravitational potential and there's kinetic. Well, it better have had enough kinetic down here so that it could loop upwards and still be traveling fast enough. Here's our conservation of energy question. The kinetic energy at the bottom of the loop has to equal the combination of the kinetic and potential at the top. Be aware, this height is 2 times the radius. They won't tell you that. You have to figure that out. This kinetic energy comes from the change in momentum that occurred due to the collision. So, mv for the bullet plus 0 for the block has to be equal to m plus m for the bullet in the block. This is a conservation of momentum problem. That's how you solve a problem like that. Again, this is the first FRQ style homework question you have. This is what it is. It's very straightforward. I've just told you how to do it. I'm not giving you the answer, but I've told you how to do it. Very much. I said that there's 2 different ways to do the ballistic pendulum problem. So let's talk about the second way to do the ballistic pendulum problem. Usually it looks something like this. Oh, come on. What are you talking about? All right. All right, so we have the before and the after. Block sitting here. Another block shot towards it. In the end, we have two blocks that have pushed against the spring and have come to rest. Do you see how this one is super similar to the pendulum one? How it's, I'm sorry, but I'm hoping you're catching that they're similar. In this problem, there's a collision that's going to take place. And it looks like it's going to be a perfectly inelastic collision because the two blocks appear to be stuck together here. So in this problem, we have a similar situation. Something probably like there's going to be momentum in the first block, and then after the collision, the two blocks will have some kind of combined velocity. Something like the middle part that I didn't draw. Where these two blocks haven't pushed against the spring yet, but now they have a combined velocity here. This part is the conservation of momentum problem. But that means these two blocks have kinetic energy, and they're eventually going to compress the spring some distance x, which means that energy is going to be converted into elastic potential energy. So the only difference between this one and the pendulum one is that at the end, the energy is not gravitational potential, but is elastic potential. Seem all right? Same kind of problem. There's more. You're going to love this one. Look on your faces is already priceless, so let's just have fun with this one. This was on not last year's exam, this is 2 years ago. So let's start with a pendulum again.